Suppose that you want to toss objects into bins. Physical bins, digital bins, doesn't matter. For example, you might want to file contacts using the first letter of the last name. Or you might want to file patient information using, say, the last 4 digits of the Social Security number. In either case, you may need to worry about what happens if multiple entries land in the same place. Okay, everybody, sit down. Oops, more students than chairs. Students on top of each other. We've just seen an example of the pigeonhole principle. There are K chairs, in this case 4. There are N students, in this case 6, and N is greater than K. So some chairs have to contain multiple students, just like the holes in this picture must contain multiple pigeons once the 10th one arrives, since there are only 9 holes. So far, the pigeonhole principle seems obvious. It turns out, however, that it can be useful in some less obvious ways. But in order to see that, we'll first formalize it. To do that, we need to rely on the notion of a one-to-one function. A function from A to B is one-to-one if and only if no 2 distinct elements of A map to the same element of B. So, for example, in the case of tired students looking for chairs, A is the students and B is the chairs. In any one-to-one mapping between students and chairs, it would not be possible for 2 distinct students to map to the same chair. So, in this picture, the mapping from students to chairs isn't one-to-one. We can now state the pigeonhole principle formally, and we can do it in 2 different ways. First way. If the number of elements in A is greater than the number of elements in B, then there exists no one-to-one function from A to B. In other words, it must be the case that at least 2 distinct elements of A do map to the same element of B. Of course, the contrapositive of this, which says that the not of the consequent implies the not of the antecedent of this claim, is equivalent to it, and sometimes it's more convenient to use, so let's just state it too. If there does exist a one-to-one function from A to B, then the number of elements in A is not greater than, in other words, is less than or equal to, the number of elements in B. The proof of the pigeonhole principle is simple. We'll do it by contradiction. Assume that the number of elements in A is greater than the number of elements in B. Now assume, contrary to our claim, that there does exist a one-to-one function from A to B. Since that function maps each distinct element of A to a distinct element of B, there must be no more elements in A than there are in B. But there are. There's now a contradiction with assumption 1. So our second assumption that a one-to-one function from A to B exists must be false. Now let's do an example where we use the pigeonhole principle to solve a problem. How many people would there have to be in a room in order to guarantee that 2 people share a birthday? To use the pigeonhole principle, we must define a set A, call it the pigeons, and a set B, call it the holes, such that our goal is to map elements of A to elements of B. Well, we want to let A be people who have to be mapped to elements of B, possible birthdays. Now the pigeonhole principle lets us recast our problem in the following way. What is the smallest value of K that makes this claim true? Well, if K is less than or equal to 366, then there exist one-to-one functions from A to B. But if K is 367, then there are more elements in A than there are in B. And so, no one-to-one function from A to B exists, and at least 2 people have to share a birthday. Now let's return to the problem of students and chairs. What if there are even more students, as there are pigeons here? Okay, everyone sit down. Now there are more than twice as many students as chairs. There have to be at least 3 students in one of the chairs. We've just seen an example of the extended pigeonhole principle. There were 4 chairs and 10 greater than 2 times 4 students. So even if we fill every chair with 2 students, someone will be left over. There's at least one chair with more than 2 students. More generally, suppose that there are k chairs and n greater than j times k students for some integer j, then even if we tried to spread the students out uniformly into the chairs, we would end up with j students in each chair and at least one student left over. So at least one chair has more than j students once everyone is seated. Let's formalize this claim. To do that, we'll make use of a function we'll call ceiling. Ceiling is a function from the reals to the natural numbers. Ceiling of x is the smallest integer n, such that x is less than or equal to n. So ceiling of 6.8 is 7. And note that ceiling of 6.0, ceiling of an actual integer, is simply itself. It's 6. Okay, now we can state the extended pigeonhole principle. Suppose that there's a function f that maps from a to b. What can we say about the crowding that we'll have to observe in b? To minimize the number of elements that are mapped to any one element of b, we should spread the elements of a out as evenly as possible. But even if we do that, there'll be at least one element of b that contains at least the number of elements of a divided by the number of elements of b. Take the ceiling of that, elements. To see why this has to be, observe that the number of elements of A divided by the number of elements of B is the average number of students per chair. But of course, we're not chopping up students, so we need an integer value. We have to use ceiling. We can't truncate downward because it's not possible that every chair has less than the average number of students. So for example, suppose there are 34 students and 5 chairs. Then at least take 34, divide by 5, take the ceiling of that, and you get 7. There are at least 7 students in at least one chair. Now, by the way, nothing in this analysis requires that we spread the students out evenly over the chairs. We could put all the students in a single chair. But then, even more dramatically, there are at least 7 students in some chair. There are, in fact, 34 in that one chair. Some chair with 7 would be our best case, but certainly not the only case. Here's another simple example. Assume that there are more than 25 million Texans, and also assume that no one has more than 200,000 hairs on the head. We want to prove that there are at least 120 Texans who have exactly the same number of head hairs. To use the pigeonhole principle to solve this problem, we have to define holes and the pigeons that will be mapped to those holes. The holes are the possible values for hair counts. There are 200,001 such values, since 0 is an option, of course. Every Texan must get mapped to exactly one of those values. Now we can make a claim about a minimum number of Texans who must share hair counts. We divide 25 million by 200,001. We get 124.99. And we take the ceiling of that, we get 125. So by the extended pigeonhole principle, we know that at least 125 Texans share a hair count. Thus, we've proved our weaker claim that at least 120 of them do. One important application of the extended pigeonhole principle is to the design of what are called hash functions. Let's go back to our opening problem, dropping names into 26-letter slots, or dropping patient records into 10,000 files. Well, here's another very common problem. Suppose that we want to build a compiler or an interpreter for some programming language. We're going to need to keep track of the identifiers, such as variable names, that have been defined, along with the information about what type they are, where they're stored, and so forth. To do that, we'll use what's called a symbol table. Assume for the moment a simplified problem in which identifiers can contain only the 26 letters of the alphabet. Well, then we could reserve one row in the table for every legal identifier, assuming that there's a maximum length. But then most rows would be empty, as you can see here. We don't want to waste that much space. So as an alternative, we could, for example, use just 26 rows, one for each letter. Then we dump the identifiers into a slot, say, based on their first letter. We'll stop wasting space, but we'll have to deal with collisions, cases where several identifiers land in the same box, as happens here in the N box. This isn't a disaster, and there are techniques for handling collisions. But to be efficient, we'd like not to cluster too many elements together in a single row. One thing we noticed, just in this simple example, by the way, is that maybe we shouldn't use the first letter. There are often patterns, and some letters are more common than others. Perhaps we'd do better, for example, to use the middle letter. But even if we come up with the cleverest of possible hash functions, the algorithms that map from identifiers to boxes, collisions may still occur. So the question we might want to ask is, how often? Well, the extended pigeonhole principle tells us something about that. Suppose that we expect that a reasonable program could use, say, 200 variable names. And let's allow for the 10 digits as well as the 26 letters, so we'll use 36 boxes. Then we have that some box must contain how many variables? Well, we take 200, divide by 36, we get 5.555. We take the ceiling of that, and we get 6. So we know we'll have at least 6 names in some box. If that's too many, then we need more boxes, and we could, for example, use, say, 36 squared boxes and assign names to boxes using, say, the middle 2 characters. We can summarize by saying that the 2 pigeonhole principles are examples of counting arguments. They help us understand what's happening when we need to map elements from one set to another set.